see if this video works. Okay, we're going to perform a little chemical reaction here, right? We're going to react sodium with chlorine. Okay? There we go. So we have in this flask chlorine gas. Look what color it is. Green. Extremely poisonous. I saw in the paper this morning. It wasn't in the paper. It was in a chemistry magazine. Chemistry magazine this morning. Somebody was cleaning the restroom or the kitchen at Buffalo Wild Wings. I didn't see what country or state it was in. But they died. They died because they suffocated from chlorine gas. This happens about every 3 years. It happens usually in hotels where there's professional cleaners constantly, doing their job. But it'll not happen as frequently, but it happens frequently enough. So as soon as it happens, everybody's like, what? Somebody died from that? That's so silly. And so they forget, or they stop doing the things that causes the problems. But then they forget about 2 or 3 years later, and somebody else dies again. So I'll tell you to help you not die, right? If you mix ammonia-containing products like Windex, right, with bleach, it'll release chlorine gas, okay? Now, when would you ever do that? It's just overzealous cleaners who think, I'm going to get this toilet so clean. Bring me the bleach, right? And so, or another thing is toilet cleaners with bleach. You got to be careful about combining those two together, right? So you don't want to combine almost any cleaners, and you don't want to combine bleach with anything else, right? But yeah, it can release a cloud of chlorine gas, and it can be enough if your face is close enough that it can kill you. So we got chlorine gas here in this container. We got a little piece of sodium metal, all right? And we're going to, oh, there it is. We're going to put this piece of sodium metal on the end of that little glass straw and put it into the chlorine gas. Now, nothing happens initially, but we'll put a little tiny drop of water on it, on the sodium, and that will make the sodium begin to react a little bit. And then after the sodium heats up a little bit, then the full reaction can occur. We have some sand at the bottom of this container here, and that's going to absorb any heat energy to prevent the glass from cracking. So here's the drop of water that's going to hit the sodium and release a little bit of heat, and then the reaction will occur. And we get white haze in there, which is our sodium chloride, right? Our sodium gas reacting with chlorine there. We get a white haze, and that's our sodium chloride, okay? What do you think? Exothermic or endothermic? Well, it looked like what? It looked like it released energy to me, right? It looked like it released energy in the form of light, and it also looked like it was getting pretty hot. They put the sand in there to keep it from cracking, right? So, exothermic reaction. But we just said that if you take an electron from, let's see, what is it? If you take an electron from sodium, does that require or release energy? What did we say? If you take an electron from sodium, does that require or release energy? Requires energy. Any family that you remove a child from, it's always going to require energy. If you give an electron to chlorine, does that require or release energy? Releases energy. Releases energy. And these are the values. Sodium, ionization energy, 495, positive, requires that much energy. Chlorine, negative 348. The net energy change between these two is a positive 146. Positive 146. So the question is, why did this process, why was it exothermic? Why was it exothermic? And the answer is Because there's another energy that's associated with this process. And it's these ions that have been formed being able to come together in this sort of a system. What did we call this? A lattice, a three-dimensional lattice. Remember how we talked about ionic compounds? How they're always found as three-dimensional lattices? Well, there's a tremendous amount of energy that is either required to separate all these ions out or released when all these ions come together in a three-dimensional lattice. Okay? And for this case, the energy associated with sodium ions and chloride ions coming together is minus 778. And so that gives us a net value of a minus 631. So energy going in or out? In. Energy needs to go in to remove that proton or electron. Energy going in or out? Out, when chlorine gets that electron. Energy going out from what? Why are we getting some more energy released? That's right. These ions are coming together to form a lattice. Okay? We call this energy a lattice energy. Lattice is good with tomatoes, right? Salad dressing, croutons, right? It's not that kind of lattice. It's a different kind of lattice, right? Three-dimensional lattice. All right, so here is an energy diagram to walk us through this chemical reaction completely. There's actually a couple other energies associated with this process. This is the energy of sodium getting rid of an electron. This is the energy of chlorine taking the electron. But here's our actual starting point. There's some energy that needs to be put in to convert sodium atoms to gaseous sodium atoms. And because solid things can't react, only the surface can. So you need to ion or atomize them, and that requires a little bit of energy. There's also energy associated with breaking chlorine gas, Cl2, into single chlorine atoms. So this energy has to go in, this energy has to go in, and then you can use the ionization energy to ionize sodium. This energy comes out, and this big one here is our what? What was this again? Our lattice energy, right? And then the net change is that energy right there. Got it? Okay. So, now, here I'm going to prepare you for a, let's see, this one? Here I'm going to prepare you for an interesting question. Okay? Someday, your kids will ask, why is it that sodium wants to give up the electron and chlorine wants to take it? Why can't we just have a free country and have sodium take the electron sometimes and chlorine give up the electron? Is that a fair question? I think it is, because I just told you that sodium and chlorine met in a bar and, sodium has a sad story. Maybe it's not true. Maybe sodium wants to be strong and say, I need one more electron. I'm going to get this electron. And chlorine says, yeah, sure, I'll give it to you. Right? Is there a universe where that occurs? Where sodium chloride is actually sodium with an extra electron, chlorine with a positive charge? All right? Well, we could follow the energetics associated with that process. And so this is what you can tell your kids. You can say, well, the problem with that is, yes, there's an energy release associated with sodium getting an electron. That's the what? What does EA stand for? Electron affinity. And there is a energy gain required associated with taking an electron from chlorine, ionization energy, right? And you will get a similar lattice energy out, but of these three, which one is going to be prohibitive? So if you just ionize the sodium and ionize or give an electron to the chlorine, that, and that results in a negative energy, right? An energy release. But if I combine these values, negative 53, positive 1251, and my negative 781, I don't get a negative value, do I? What's prohibitive in that process? What is so energetically unfavorable about doing this reaction? Okay, here's the chemical reaction. You ready for it? Sodium atoms plus chlorine ion atoms. And we're going to make sodium get an electron and chlorine lose an electron and form this compound. What is happening for sodium to get an electron? What energy is associated with this? What do we call that? That's electron affinity. How much energy is that going to require or release energy? It releases. Every family will take one kid, right? So how much energy does that release? Negative what? 53. That's right, a negative 53. That's the electron affinity associated for sodium. Okay? It's going to require or release energy to remove a child from chlorine's family. Requires energy. How much? Yeah, 1,251. There it is. That's the energy associated with removing a child from chlorine. And then to form the lattice energy, how much energy is that going to, what is it going to require or release energy when you form the lattice energy? It always releases. How much is it going to release? Yeah, negative 787. So we got the negative 787, we got the positive 1,251, and we got the negative 53. Is the result of that going to be a positive or a negative number? Positive. That's right. So when your child says, why can't we have a free world and sodium get the electron and chlorine give it up? You say, what? What are you going to say? Good idea. Let's just give it a shot. Is that what we're going to say? No. What are we going to say? The ionization energy of chlorine is just too high, honey. Right? That's what you're going to say. Okay. So, again, we're boiling the wants and needs of atoms down to actual energies, right? This is our energy associated with the formation of a three-dimensional lattice. You take the charge of one of the ions and the charge of the other ions, multiply them together, here's a constant, and R is the distance between those atoms. So, here's a positively charged ion, here's a negatively charged ion. The closer they can get, the stronger the lattice energy will be. All right? What else will make this energy large? Close radius, right? Small number in the denominator. If we have a large charge, +2, -2. Have you guys ever sat and just looked at the solubility rules and wondered why certain compounds are soluble and ones are not soluble? It'll happen someday, right? You'll be sitting there looking at the solubility rules and say, hey, why is this one not soluble? And what you'll find is usually the ones who aren't soluble have large charges, like a +2, combining with an ion that has a -2, right? Because the resulting lattice energy is so high, it's hard for water to overcome that lattice energy, right? Okay, lattice energy. Now this is stuff that we've already kind of gone over. Now, identifying the electron configuration of ions wasn't part of the previous chapter, but because it was kind of right there, we did it already. So this is just a review. But if you take the electron configuration of sodium, 3s1 will be our valence electron. So in a sodium with a positive charge will lose that valence electron. Okay? Should we do one practice? Can you guys identify the valence or the electron configuration for the magnesium ion? Mg plus. What's the electron configuration for the magnesium plus? Whoops, it's going to be a +2 charge. What's the electron configuration for the Mg plus ion? This is easy peasy, right? We can use noble gas electron configuration. Electron configuration for the magnesium ion. Did you get it? Start with the magnesium metal if you want to. Again, noble gas electron configuration. Did you guys get it? Good. Neon. That's the electron configuration just for the magnesium atom. And if you want to make it the ion, what do you got to do? You just remove 2 electrons, right? Remove the 2 electrons that have the highest energy. What is it? Is that it? The noble gas electron configuration of magnesium is a neon atom, right? Does that make sense? So maybe we should write the noble gas electron configuration of the magnesium atom to start it off with. Right? So magnesium starts with 2 valence electrons. Its ion doesn't have those valence electrons. Okay? Maybe one more. Electron configuration for the chloride ion, Cl minus. Chloride ion. This is kind of tricky because if you go neon is your noble gas core, right? Then you got 3s2, 3p, what? But we're looking not for chlorine atom, but chlorine ion. Is that adding an electron or losing an electron or adding an electron? Yeah. 3p6, which is also argon, right? Does that make sense? And that's why chlorine is always in situations where it likes to take one more electron.
Is argon a gas?
No. It is inert, or sorry, it's you can't breathe it and live, like helium, right? But it's not poisonous in terms of a very small amount won't kill you.
So for the noble gas configuration, would you have to divide it into neon and all that stuff for heating?
Yeah, so the electron configuration for a noble gas.
Or, you know, for like the...
Oh, for the ion, the negative ion?
Yeah, would they have to do neon and then
Yeah, I don't know. They won't ask you to do that sort of thing. We were just kind of figuring it out. Yeah, either one should be right answers. So if they give you both of those, that would be a bad question. Atom stability also comes from full or exactly half full sublevels. I think we already talked about that, but we can use some examples. So, let's see here. Let's predict, we've already done this once with iron, but let's predict the ions from our electron configurations that should exist for iron, zinc, and thallium. So essentially what we're going to do is write the electron configuration, and then we're going to look for valence electrons, and then we're going to look for ways to make the subshells half full or full. All right? So if you don't understand what I'm talking about, then why don't we start with just our noble gas electron configurations for these atoms. Okay? Noble gas electron configurations for iron, first of all. Noble gas electron configuration for iron. Argon, right? Argon. What's after argon? What row is potassium in? 4. And it's in the what block? S block. 4s2, 3d6. Great. Go ahead and write the electron configurations for the other two while you're at it. Zinc, 4s2, 3d what? 10 for zinc. Thallium. Thallium's a bugger. Why is thallium a bugger? 6s2, is that right? Thallium, 6s2. So what's the core for thallium? Xenon, 6s2. And then what's after 6s2?
5D.
Before you go to 5D, what happens first? Yeah, that F block. Have you guys had any practice problems working with F yet? Here's a surprise for you. This isn't 5F. It's not 5F. What do you think it is? No. This wasn't 4D. What was this? 3. This isn't 5F. Let's see. What should it be right here? 6. 1, 2, 3, 4, 5, 6. It's not 5F. It's 4F. 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 How many electrons should be across in the 4F? You'll always have a periodic table, so you can always count. But if you're talking about the F block, then that means L equals what? What does L equal? There's S, P, D, and F, so it's 0, 1, 2, and what? 3. L equals 3. If L equals 3, what are the possible M sub L values? -3, -2, -1, 0, 1, 2, 3. So that's a total of 1, 2, 3, 4, 5, 6, 7. So each one of those represents an orbital. And for each orbital, there's going to be a possibility of a positive 1/2, negative 1/2. So there's a total of 14 electrons across there. And you can always count them on the periodic table. Okay, so for thallium, what is that? Xenon, 6s2, 4f14, and then what? 5d10 and 6p1. Okay, very good. So starting off with iron, what are we going to do to form an iron or an ion from iron? Take the valency electrons and form a +2 charge. Very good. So that is one of the ions that will form for iron. And we've already talked about this one as well. How did we say another ion might form? By doing what? Or maybe you just remember. What is the other ion that iron forms? It forms a +2, but it also forms a what? +3. So that would be removing another d electron. Why would we want to remove another? Why would iron find stability by removing another or a d electron? What would that leave behind? That's right. If it's 3s, sorry. 3s, no, 4s, that's right. 4s, 3d, right? 1, 2, 3, 4, 5. This is what iron looked like. 1, 2, 3, 4, 5, 6. There's iron. We remove these ones because of the highest energy. So that's an iron +2. And when we remove that one, it makes the ugly cousin handsome, right? Does that make sense? So now this is a +3 ion because we removed 3 electrons. Okay, so let's finish up these other ones before we leave. What do you think? Looking at zinc, what kind of ions do you think it would like to form? +2, that's right. It forms a +2 ion by getting rid of 2 of its valence electrons. Any other ions? No. If it were to lose more electrons, how many would it have to lose? 5 to get a half-filled subshell. But that's the way it is. Zinc is only found as a +2 ion because it's just too much energy to release another 5. Thallium, what do you think? What's thallium going to do? Okay, it does a +1 by losing the 6p, and it also does a +3 by losing 2 additional 6s's. Does that make sense? So now this is less predictive and more explanatory, right? So you look at thallium and you say, oh, that's why it forms a +1 and a +2 or +3 ion. Okay, very good, guys.
Wait, can you?
Want to look at that some more?
Yeah.
Is that big enough or should I make it bigger?
Okay.
So thallium could do a +1 or +3. Why couldn't it do a +2?
That's a good question. That's a good question. And I'll bet it does do a +2. I'll bet it does. I'll bet it does do a +2. So, you know, I don't know what all the charge states are for thallium. Let's look it up. What are the charge states for thallium?